Hello students, in this video we will find out how to solve a pair of simultaneous equations, linear equations, graphically. So this is a follow-up to the week 4 discussion assignment in which I illustrated a particular example here, right? You may remember that we had two equations where x was the number of pieces of cake and y the number of pieces of brownies or number of brownies. And then our constraints on the equations were the total weight of the cake plus brownies, and the second constraint was the total cost of the cake plus brownies. And so we had these two equations. So this is the model. Now let's figure out what we can get by putting in some numbers for these things. Okay, so that's what I'm going to do over here. This graph is available at the link that I posted in the discussion assignment. And the problem is already set up over here in the following form. This is a linear equation, right, for the variables x and y. This is with one of the constraints, and the second equation is here. Now the values of the constraints and the coefficients can be set via these sliders. You have to remember here that what we are trying to find out is the values of x and y. And in this particular example that we're going to do, x refers to the count of the number of pieces of cake that I can get, and y is the count of brownies that I can get when they're subject to a constraint on the total weight of the two things together of being 8 ounces and the total cost being $10 or less, right? So let's see if we can enter in the numbers. So one of the things that you will notice is that this is a handy technique for simply playing around with equations and finding their solutions. So I'll put in the constraints first, remember, and I'll use ounces as the units because that's what we had talked about in the example, right? So if you remember, that was 8 ounces and our total cost was $10, right? So I've set those numbers. Now comes the fun part when I try to change the values of the coefficients. So if you remember, A is supposed to be the weight of one piece of cake and B is supposed to be the weight of one brownie in ounces. So right now they're set at numbers which are not showing much of anything, but as you move the coefficients around or the sliders around that represent the coefficients, you'll have equations that begin to show up. So this is the first equation, and I'm going to move the slider C for the second equation just to make it appear. Now at this point, what you're seeing on the screen is there is a solution way back here, right? But it's occurring at where the value of x is going to be 10. And anyway, what I would like to see is find out a solution which is a bit more realistic and in this region here, simply because I can demonstrate it more easily, okay? And right now, this wouldn't have been a correct solution either, because you can see that the value of the slider is a B, which represents the weight of a brownie, is negative. You know, how can you have a thing with negative weight, which is not possible within this space-time continuum? Let's just put it that way, okay? So we'll make the weight positive for that thing as well, and that will change the equation, as you can see. Similarly, in this case, we'll make the weight a little bit more realistic, and now we're getting somewhere. Now the two lines are intersecting each other, right? So in this point of intersection is the point which simultaneously satisfies both equations. And that was our objective in that week 4 discussion assignment was, can we find a pair of values, x and y, that will simultaneously satisfy two constraints? Okay, so I have a solution here, which basically with these values as represented here, is saying, okay, I can have, what was our x? X was the weight of one piece of cake, or actually x was the count, the number of pieces of cake. And so here x is 1.85 and y was the count of brownies, and that's 1.43 roughly. And you're going to say, wait, how are you splitting these up? Well, you know, the baker happens to be very friendly, right? And so they don't mind slicing a piece of cake into a smaller portion and so forth, and a brownie. But let's be more real. Let's retain integer counts for the pieces of cake and brownies. So you can play around with these equations. This is the nice thing. So I'm going to try and just play around with this a little bit and see if I can get the solutions to kind of line up to more to integers for a and b. Well, I got b equal to 3 over here. A is not quite there, but I'm going to play around with this a little bit more, and then we'll see where we get to. Okay. Obviously, you know that I've played around with these beforehand, so I know what values to set them to. But I'm doing this so you can follow along with the process. And then there's one other important piece to note. Okay, and that is that since we're dealing with physically real things, our solution has to be realistic. Right now, these two equations are intersecting, but note where the intersection occurs. It occurs at a negative value of x. And just like I was saying to you earlier, we can't have a negative weight. We can't, if you're going to go to a bakery and buy things, we can't have a negative count. You know, that means we are trying to give something to the bakery or sell something to the bakery. Well, you know, maybe that can happen, but it's not very realistic for our example. So the important thing to note is if your solution, as you vary the constraints and the coefficients, if the lines intersect in these regions, these shaded regions, okay, that means that the solution is not physically realistic. Your solution must lie in this unshaded region, the white space over here, okay? So the lines must intersect in this region, okay, in order for the solution to be realistic, physically realistic, okay? So let's play around with the variables a little bit more. I'm going to leave the constraints set at 8 and 10 because that's what we use in the example, and I'm simply going to fiddle around with the values of the sliders. So let me see, oh, here, now we're getting somewhere more realistic. At least I have a solution in the space where it can be real. So I've got something over here. Now let's see what else can I do. So I can try and move this slider a little bit. Nope. Well, it's realistic, but it's disappearing from view. So let's see. I can leave this at, can I get to 2? Yeah, please. All right, getting close here. I have difficulty setting the values of these sliders, but close enough. You can do this yourself, or I can simply click in here and just make it 2, right? That's another way of doing it. So I got a value of 2 and 4, and it looks like I'm coming close to a particular point over here. So let me see what I can do, and I'll move this one around. Move C. Oops, no, that doesn't get me anywhere. So let's see if we can move this one to 2 as well. Okay, and no, now there's no solution at all. So I'm going to go back and fiddle with the sliders. There's no particular method for this. You can fiddle around with these any way you like till you get to a solution that you like, which is the nice part. And so, oh, hey, now we've got a solution, right? The two lines are intersecting in the space where physically realistic solutions are possible. And look at this, right? Here's the point of intersection, and guess what? We've got integer values for x and y. So I can get 1 piece of cake and 2 brownies because x represented the number of pieces of cake and y represent the number of brownies with the following constraints. The combined weight of all the pieces together, so 1 piece of cake and 2 brownies, is going to be 8 ounces or less, and the cost of that 1 piece of cake and 2 brownies is going to be $10 or less. Remember, we set the values of the coefficients. So A, which is the weight of 1 piece of cake, is 2 ounces, and the weight of 1 brownie is 3 ounces, as represented by B. Similarly, the cost of 1 piece of cake is $2, which is C, and the cost of 1 brownie is $4. Now you can plug the values back into the equations and see that both sides balance, and so, you know, it all works out. You may have a quibble about why is it the brownies are more expensive and heavier than the cake. Well, they always seem heavier than cake to me, and I don't know, maybe this is a secret recipe that the baker has, and so these are very, very special brownies. It just works out that way. Play around with these things, and with the creative problem that you set up. Don't just replicate this problem. We've already solved it. There's not much of interest left here. So try and find something where you don't know the values of the variables x and y, and something that relates to what you do in your real life or at work, and see what you can come up with. Okay, let me know if you have any questions. Again, paste your questions to the forum, or post your questions to the forum, or email me directly, and I'll see you on the forum. Bye now.